Shall we start?
Yeah, we should start. Can you share the screen? Okay.
Yeah.
Cool.
Yeah, can you see the screen?
Yeah, it's visible.
Okay. All right. So it's a continuation of the first lecture. So in the first lecture, am I audible, right?
Yeah, you are audible.
Okay. All right. So in the first lecture, we defined the exact category, and so exact category is an additive category. With adjust structure. So as an example of adjust category, last time we discussed that category of projective R module, finally generated projective R module, and also MR, finally generated R module. So these are actually example of adjust category, and we consider we define both K0 of PR as K0 of R or K0 of MR. So it's G0 of R. Okay. And in fact, even for a scheme, Quasi compact may be Quasi separated. Then we take the vector bundle over X. And MX is category of coherent OX module. Then we also define, we both are again exact category. Then we define K0 of vector bundle of X, just a K0 of X, and G0, so K0 of MX is known as G0 of X, this is G theory. Okay, so we prove a theorem if R is or X is regular Northern scheme, then K theory and G theory coincides. That is the theorem we proved last time, and we proved a categorical version, but as a consequence of the of our theorem is just this corollary. If X is a regular Northern scheme, then authentic group of X and G theory of X coincides. G0 of X. Okay. So now we'll see the higher K theory analog. This follow this theorem. Okay. Today's lecture. Okay. So for that we need to define a higher K groups. But okay, we'll just give an overview of how to define higher K groups. So more general way to define is called Waldhausen S-DOS construction. So it's already been defined, I think, Waldhausen category. So what is Waldhausen category? So it's a kind of is a category category C with zero object. So category with zero object, which has both initial. Zero object means the object which is both initial and terminal. And last time we discussed. And two distinguished class of morphism. OC and WC. This is called the co-fibration. And this is called weak equivalence. Satisfying certain properties. Okay, so I'm not going to give the details because this has already been defined in some lecture. Okay, so in the abelian category, so remark. So it's a generalization of kind of exact category. So note that in abelian category, what are the morphisms? Suppose in abelian, the monomorphisms are co-fibration in any abelian category. Okay. So any abelian category is a category with co-fibration. So what we demand in the Walderson category of co-fibration means the monomorphisms are actually plays role as a co-fibration in abelian category. And in an exact category, admissible monics. Last time we defined what is admissible monic and all this. Monics are co-fibration. So any exact category is a category with co-fibration. And what is the weak equivalence? So this is the minimal choice of equivalence, all isomorphisms. In C, in the category C. So weak equivalence, if you take all the isomorphisms, then it satisfies the certain properties which we actually expect. So this is the minimal choice of weak equivalence. So basically, what is the which is implied that any exact category is in one-Hausen category. By choosing admissible monic as in co-fibration and all isomorphism as in weak equivalence. All right. But so that means Walderson category actually the more general setting. So you can see that in Walderson category, we are not assuming your category is additive. So we are just only start with the category with zero object. So there are non-additive exact category. So there are non-additive categories which are maybe Walderson but not exact. But in exact category definition, you can see start with an additive category. But in Walderson category, we are actually in more general setting. So it covers more categories in Walderson category. So more general. Where I'm not assuming a category start with a additive category. I'm just assuming they start with a category with zero object. So this is the fundamental difference between Walderson and exact category. Okay. So basically, of course, any exact category is always Walderson. So our known example, vector bundle over X, coherent module over X, also are exact category as well as Walderson. But there are some topological categories. There are some examples, but I'm not going to discuss this in the lecture, which are actually Walderson but not exact. So mostly you have to choose some non-additive category. Yeah. Okay. 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 Now actually, basically now Walderson has some different hierarchy groups. So basically, hierarchy group there are many constructions. Initially, first start with the class construction of cooling, but the class construction only keep a category of hierarchy groups of rings. And then Quillin again define a Q construction. So that basically define a K theory of all exact categories. But then one has to generalize it in more general setting. So K theory of Waldensian category, that means it's cover more larger settings. Exact category plus more some categories maybe which is not in additive in nature, but which satisfy certain collaboration and equivalence properties. Okay. So what does an S-DOS construction? This is the one of the general construction of hierarchy theory. Waldhausen S-DOS construction. So basically, we have already K0 of C. Then how to define a hierarchy theory? So there is a formalism. You can define a S dot C. So that is the S dot construction. So that we need one lecture to explain. But strictly as a black box. So what is this S dot C? It's a simple cell category. In fact, simplicity and word version category with WS dot C, a simple shell with equivalence. Okay. So basically, given a start with the category and apply the formalism of Waldhausen, S dot formalism, and then we get S dot C. This is a simple shell Waldhausen category. And what you do, then there is a natural way to get a topological space. So take the geometric realization. So that is okay. And then consider say this is topological space. In fact, it's a connected topological space. One can check it. Okay. So then the fact, if you consider the pi one of this, the geometric realization, then this is canonically isomorphic to K0 of C. Okay. And the higher K groups, the K groups, of C are defined as for okay. So homotopy group of this topology space. Okay. So from the definition, you can see this definition of K groups actually given by homotopy groups. So it's very difficult to come. Okay. So in the study, so that is about the Waldensian category. But any exact category, suppose this N is an exact category. Then any exact category can be thought is an Waldhausen category with equivalence all isomorphism. Okay, so this is a natural way to construct a Waldhausen, natural way to think a exact category is Waldhausen. Okay, so then so hierarchy groups of exact category is a similar fashion by n of okay. Or, so now how K theory of exact category is defined, but again it's in terms of homotopy theory. So but so this is one of the fundamental problem in K theory that higher K groups are not they're not very easy to calculate because in definition in nature because it's a homotopy groups of certain topology space. So Grayson has a new idea in recently in 2012. So what Grayson did, Grayson defined a hierarchy groups totally algebraically. Okay. So today's talk probably I will recall first Grayson algebraic description of K group. So this is a totally homotopy theoretic definition of hierarchy groups. Okay, so now Gerson has an alternate approach to define a hierarchy groups algebraically, and at the end, the Gerson's main result is the following: that his groups and the groups just have defined are canonically isomorphic. So basically, one can take alternate approach of Gerson to calculate K groups or to prove certain theorem of K theory. Okay, so in today's talk, probably I will. Okay, so most of the time I'll spend to describe Grayson new description of K groups. That is relatively new. So this description is around 1970 or 80, and Grayson's description is comparatively new in 2012. All right, so here is a Grayson description. So Grayson algebraic description of K groups. Okay, so here is a reference for this. Algebraic K theory via binary complex. Complexes. And this is, I think, James paper 2012. Okay, so most of the so whatever I am going to discuss based on this paper. Okay, so so what Grayson defined K theory of exact category algebraic. K theory of algebraic. Basically via the binary complex. So we have to define what is binary complex and all this. So for that we first need to define long exact sequence in a general exact category. So in abelian category, a long exact sequence is nicely defined because you have a notion of kernel co-kernel. But in an exact category, we really don't have usual sense sorry exact sequence. We have to impose some structure so that we have a similar notion of short exact sequence. So first we have to make sense of long exact sequence in general exact category. So we first need to define long exact sequence in a general exact category. Okay. So we have seen that what are the because kernel co-kernel pair usually called as short exact sequence in exact category. But now we have to make sense of long exact sequence. So throughout n denotes an exact category. So whenever I am saying exact category, you should always keep in mind category of vector bundle order X or category of finely generated positive R model in your mind, or category of finely generated R model. If you have a difficulty to think exact category, general exact category. Okay. So what is the chain complex? A chain complex in an exact category is n dot and di, where n dot is a z graded collection of objects, and di is a collection of morphism from ni to ni minus 1 such that the composition is identical for all I. So a chain complex in a category N is just a collection of z-graded objects. There may be some negative terminal complex and collection of morphism from ni to ni minus 1 such that the di minus 1 times gy is 0. So these are definition of chain complex. Okay. And bounded chain complex means it has a finitely many objects that are non-zero. So bounded means means only finitely many of, of the objects are non-zero. Okay, and basically chain map between two chain complex is a sequence of maps which commute to the differential. Okay, so basically now we have a category Cn, the category of bounded chain complexes in an exact category. So because we have a notion of a chain complex, we have a notion of morphisms, so it forms a category. Of course, one has to check the properties, but yeah, it is a category and it is a category of bounded chain complexes in a exact category N. So fact, Cn is an exact category. Okay, so why this is an exact category? Because you remember last lecture that given any exact category that always embedded in a abelian category, right? There is one lemma we stated, right? This is a Gabriel-Quillian theorems. Okay. And if A is abelian, then corresponding associated chain complexes is also abelian. That is a standard result in homological algebra. Start with the abelian category and the chain complexes in abelian category is also an abelian category. And then you have a similar embedding here, Cn equals to A. And as long as every abelian category is exact category, so the exact structure induced from Ca. So basically then Cn is exact category. And we also see one lemma that suppose n is a subcategory of a M and M is exact, then n is also exact with the induced structure. So in that sense, Cn is also exact. Okay. So this is the idea of the group. So any category of bounded chain complex in an exact category is also again an exact category. Okay. So now we have a notion of an exact chain complex in an exact category. Now remember in an abelian category, in an abelian category, a chain complex is long edged or acyclic if so you have a type notion of kernel, right, in this abelian category. Kernel of di I minus 1 is same as image of di for every I, which is equivalent to saying that cohomology of this chain complexes is 0 for I get equals to 0, and that is also equivalent to saying quasi isomorphic to C dot is quasi isomorphic to 0 complex. So that is the definition of a long edged sequence or acyclic chain complex in the settings of abelian category. Okay. So suppose given a given a chain complex in abelian category, okay, and you have a differential di plus 1 So what is the meaning? Is a long-edged sequence? Suppose this is a long-edged sequence in abelian category. Then what does mean that? This means this implies kernel of di minus 1. Sorry. Kernel of di same as image of di plus 1. Okay. So let Zeta is kernel of di and which is same as image of. So this is a long-edged sequence in an abelian category. Okay. So then this long-edged sequence splits into a short-edged sequence in the following way. This short-edged sequence in the abelian category. Okay. All right. And this is di. Am I audible, right?
Yeah.
Okay. So given a long-edged sequence in abelian category, you can split into a short-edged sequence. So in fact, we have the following factorization. In fact, we have the following factorization that ai to ai minus 1. So we have a and then again similar way. Okay, so you have this following factorization. Okay, so this factorization leads to a definition of long-edged sequence in exact category. So given a long-edged sequence in abelian category, we have always have this following factorization. That means you can split a long-edged sequence into a short-edged sequence. Okay, so this leads to a definition of a long-edged sequence in a general edged category. So now what is the definition of chain complex in general edged category? So a chain complex yet in an exact category and is long-edged sequence or acyclic if there exist objects Zi of n such that the differential factors through Zi via short-edged sequence in the following way. So basically, what they are saying, they are doing a chain complex is said to be a acyclic. You have the following factorization. So this is a Zi. This is additional monic, and then again this is a epi, and this is additional monic. So you have this following factorization. Okay. Such that there exists object Zi, such that this factorization always exists. Then a chain complex is said to be long-edged sequence. So that is basically generalization of long-edged sequence in an abelian category. So note that if your category is abelian, this factorization always exists. Okay, so that definition your definition for long exact sequence in the settings of abelian category also satisfied here, because any abelian category is exact category. So that is the definition of long exact sequence in the general exact category. So there are objects Jedi such that this factorization hold always. That means these are adversarial monic and these are arithmetic equivalent. So the kernel co-kernel pair basically. All right. So in this setting, so now we have a notion of a long exact sequence or acyclic chain complex in the settings of exact category. All right. And we denote these things CQN in the category of bounded acyclic chain complexes. So of course CQN certainly is treated as CN because CN is a category of bounded complex. Now we restrict the category of bounded acyclic chain complexes. Okay. And again another is that CQN is also an exact category. Also, it's still the exact structure remains same. It's not a problem. Okay, because okay. So note that. So since Cn and CQn both are exact, so note that we start with the exact category n, then we construct a Cn category of bounded chain complexes and CQn category of acyclically bounded chain complexes, and what we get start with the exact category. Still we are in exact category. So both are still exact category. So we can iterate this process. We can iterate the process, the procedure to get C times n. That means you apply C n times. So that is basically bounded n-dimensional multi-complex. Start with this n, then apply C. This is again exact category. Then again apply consider chain complex of chain complexes. Then that is C2n. Then you iterate this process. So you get a CNN. Just you are applying C n times. So basically you get bounded n-dimensional multi-complex. So similarly, we have a CQ times n times means you are applying CQ. So acyclic bounded n-dimensional multi-complex. Okay, for n equals to 2, you can see how it looks like. So n equals to 2, it looks like this. Okay, because you are considering chain complex of chain complexes, right? And for n equals to 2, it looks like a cube, right? Then another chain complex you have. And you have another map here. So basically, in n equals to 3, the C3n it looks like a cube, and C4n looks like a tetrahedron, so on and so forth. Okay, so basically, so it's a huge diagram, but at least you understand the framework. So given a exact category, you can always consider the n-dimensional multi-complex. Okay, so that is about the chain complex, and still are there exact category. Okay, now we'll come to the point, the binary chain complex. Okay. So a binary chain complex in an exact category N is a triple Okay, such that so basically it's a chain complex with two differential, top differential, bottom differential. Okay, so it's a triple. It's a chain complex with two differential. N dot d prime. Okay, so what is the stupid example of a binary chain complex? Of course, take any chain complex and take the similar differential. I did not say d and d prime are different. They may be same. Okay, if it is d, then you take d, d. Both are actually same differential. Or take suppose p and q in PR in category of finite general positive R module, and suppose you have a two isomorphism between p and q. Then p alpha and beta. So this is a binary complex because it's a. Of course, you can think as a chain complex, right? Because everything is here zero. Alpha and beta are isomorphisms. And you also think is an actually a differential, right? So this is a stupid way to construct an example of a binary chain complex. So this is also a binary chain complex. Okay, so basically binary chain complex means is a chain complex with two differential. They may be equal. All right. And of course I'm assuming the chain complex are bounded because Cn, because n dot d and the prime is in Cn. So in fact, this again the morphism between two binary complex is again a chain map, the chain map which commute to the both the differential in a natural way, correct? So now we have a category of, so now Bn, the category of bounded binary complexes in N. Okay. We say that a binary complex is diagonal if d equals to d prime. As I said that this is a stupid way to construct uh, binary complex, that if you take both the differential equal, then this kind of binary complex will be diagonal. Okay. So there are exact functor. There are exact functor. So one is diagonal to Cn to Bn. With any chain complex, you can thought as a binary chain complex by duplicating the differential, by sending nd to ndd. Okay. And there is a top functor. So T Bn to Cn. So basically you are forgetting the top differential. And this is a bottom functor. Okay. Okay. So note that delta is split by top and bottom. Naturally, because you are just forgetting the top differential and then you are just mimicking the duplicating the differential. So you get the same outputs. All right. So basically this top and bottom gives a functor from Bn to Cn cross Cn. So n dot d prime, you're just sending n dot d to n dot d prime. Okay. So basically, a binary complex you can think as a pair of the chain complexes. All right. So we call a binary complex is acyclic. Okay, if its image under both T is an acyclic chain complex. So we have already made sense of acyclicity in the settings of exact category, right? So when we say a binary complex is acyclic, that means under the image of this top functor and bottom functor, the resulting chain complex is an acyclic. Okay, so these two are acyclic. Then we say that binary complex is acyclic chain complex. All right. So in similar fashion, you can define BQN, the category of a bounded acyclic chain complexes. Now here is a fact. Again, that Bn and BQN both are exact category. So that exactness checked by this using these two functor, top and bottom functor. Because anyway, if you apply this top and bottom functor, you will land to the chain complexes. Okay, so even both are exact. So again, this is similar fashion. By iterating the process, you can consider the n-dimensional binary complexes and n-dimensional acyclic binary complexes. So by iterating, because Bn and Bqn both are exact categories, so you can iterate this process. Then we have Bnn and BQN, right? Okay. So what are the object in BQN? So an object BQ is a n-dimensional bounded acyclic binary multi-complex in an object of Bn complex, which is a Zn graded object collection of objects of n together with a pair of acyclic differentials di and d delta I in each direction. Note that for n equals to 2, you have this looks like a square, right? So you have two directions. So you have a differential in two directions. So similarly, in n equals to 3, you have a difference in the three direction, so on and so forth, in n equals to 4. So you have a together with a pair of acyclic differential in each direction with such that differential in different direction commutes. Because in the different direction, differential is actually connected by a chain map, right? It must commute with the other differential also. So basically, for n equals to 2, it typically looks like C11, C10. Then you have another here, C01, C00. So here actually DI, D tilde I, again DI, D tilde I, so DI, D tilde I. Okay. So therefore n equals to 2. So similarly, n equals to 3 looks like a cube, and so on and so forth. Okay. So this is a n-dimensional binary complexes. Okay, with a differentiality with two differential in each direction. All right. So we said that an object of BQN in N is diagonal is a diagonal binary multi-complex if the differential di and di tilde I are identical for some I. So when you say that n-dimensional binary multi-complex is diagonal, if in one of the direction, at least in one of the direction that differential are identical. Like in one of the direction, it looks like a chain complex because both the differential are actually identical. So then we say this kind of binary multi-complex is called the diagonal. So you remember in the for n equals to 1, you just only have a one direction. So that means just d equals to d prime. We have already given the definition for that. Okay. So for n dimensional means at least one of the direction differential are identical. Then we say the diagonal variable. Okay. All right. So since BQN is adjust category, we can define, and we are already defined for the K3 for K0 for the exact category, right? Since BQN is in exact category, so we can define K0 of these things, right? No harm. But this definition makes sense because whatever these groups that we do not know, but at least the definition makes sense because BQN is an exact category. So and that definition we already defined for the exact category for K3. K0 of exact category we have already. So this makes sense. All right. So what Grayson defined? So definition due to Grayson, there is one of the. So what is the Grayson's group? So let N be an exact category for all n greater equals to 0. The nth K group Kn. I'm writing intentionally for Grayson for Kn grade. N is the abelian group having generator one for each n dot belongs to BQNN, and relations are for every. So as you remember, the BQN is a exact category. So you have a notion of sort exact sequence, right? Kernel co-kernel pair. Okay, so this is actually exactly the K0 of K group, right? That we have defined. So it's generated by free abelian group generated by each of the object modulo this relation. And not only that, he imposed one more condition. The condition 2 is the following: that they consider all the diagonal elements as 0 in this group. So if T is a diagonal acyclic binary multicomplex. So Grayson defined higher K groups in the following way. It's a free group generated by each of the objects modulo these two relations. First relation is the same as the A0 group, and he imposed one more relation that he consider all the diagonal multicomplex as 0 in this group. Okay. So remark. So let T and N denote the subgroup of K0, BQ, and N generated by K0 classes of all diagonal multicomplex. In BQN. So consider all the diagonal binary multicomplexes of K0 class and take the subgroup generated by this thing. So that T and N is a subgroup of K0 BQN. So then from the definition, it's very clear that K0 crescents, Kn crescents is isomorphic to K0 BQN and modulo this group subgroup. So what is the advantage of the Grayson's definition? Grayson's advantage is that the higher K theory you can view as a portion of a quotient. Okay. So this is the advantage of the Grayson's definition, that you can view a higher K groups in terms of quotient group, basically the quotient of a quotient group, right? So then the seminal theorem, the fundamental theorem of Grayson says that theorem. In the same paper, he proved the following. So unless these are coincident to the old classical definition, there is no make sense, right? So for an exact category, and the definition the Grayson gave is isomorphic to the definition I have defined in the beginning. Okay. So that is the main theorem of the Grayson's paper, that he defined a K theory algebraically, and then he proved that whatever the K group he has defined, that coincide, that actually naturally isomorphic to the classical definition. Okay. And what is the advantage of the Grayson's definition? The Grayson's definition is totally algebraic. There is no homotopy theory. In the proof, to prove this theorem, there are lots of homotopy theories. But at the end, to calculation of the K groups, there is no homotopy involved. It's totally algebraic, okay, and totally formal. So Grayson's K groups actually basically you can think as a question of a quotient group. All right. So using this Grayson technique, we can prove our resolution theorem for higher K groups. Is that definition clear?
I hope yes.
Okay. So we'll finish by giving the sketch of the proof, the resolution theorem. All right, so just remember the theorem last time we did that rho is a full subcategory of a exact category M. This is an exact category, right? And also this is a closed under extension. We assume the following thing also. So rho is a exact subcategory of an additive subcategory of an exact category M, which is closed under extension. Okay, and such that we have two conditions. We also assume that for any exact sequence, in M, if P is in rho, then P prime is in rho. So this is a little bit stronger than the closed under kernel, if you remember last time. And second is for any M in M, there exists a P in rho such that P there is admissible monic epic from P to M. So basically this defines a finite positive resolution for every element of them. So in these settings, then the theorem claim that K and M is asymptotic to K and M for N greater or equal to 0. And we prove it for K0, right? Now our goal is to prove it for higher K2. So note that using Grayson's technique by Grayson's, what is this? This is the K0 of BQ n rho modulo T n rho. And what is this? K0 of BQ n M and modulo this diagonal part n n. So basically I want to prove the isomorphism between two groups, right? Okay, so what is the natural constant? We have to define an isomorphism between K0 level, and then we check if the isomorphism level descends to that respect these quotients or not. That's the idea. So basically the proof of the K0, what we prove in the K0 level, that proof will go through with some checking. Okay. So what I have to check? I want to prove this isomorphism, right? So basically I want to check whether the hypothesis of the theorem still carry forward to the binary complex level or not. So what is the sketch of the proof? Whether if you want to put a higher K3 level, it's enough to prove these maps are actually isomorphic, these maps. Okay, so sketch of the proof. First what I have to check, if rho is closed under extension in M, then so is BQ in rho. Okay, if rho is closed under extension in M, then the binary complex level is also a closed under extension. That first you have to check. Second thing, you have to check if the inclusion. So this is the first line of the theorem, right? That rho is a subcategory of exact category M and closed under extension. The second thing, if the inclusion rho sitting inside M satisfy the hypothesis one, then so does the inclusion. Okay, so that is the hypothesis one. If rho satisfies the hypothesis rho inclusion M satisfies the hypothesis one, then so does this binary complex. And then third, now we have to check the second hypothesis. So that is the following. If so, that is the proposition. Let rho and M satisfy the hypothesis of the theorem. The hypothesis one and two. Then what is part A? For every there exists a shortage sequence in BQM with okay. So that is the second property. You can remember that. So for every object of M, there is a finite positive resolution. That is the second property. Basically, this verifies the second part of this second hypothesis in the level of binary complexes. And the second, okay, and what is the second part of this proposition? That if M dot is diagonal, then one can choose P dot and P dot prime also diagonal. So what is the second part state? Suppose this in shortage sequence M dot is a diagonal, then we can choose P dot and P dot and P dot prime is also diagonal. Okay. All right, then. So in view of above proposition, what we have? We have K0 of BQN rho is isomorphic to K0 of BQN M for each N. So because we have already proved this theorem for K0 and we have already verified that in the binary complex levels also these all hypotheses are actually holds. So that's why I'm assuming, so then the K0 of BQN rho and isomorphic to K0 of BQN M for every M. Now what we have to check? We have to check that, and these Kn groups are actually modulo the diagonal part, whether this isomorphism respects the diagonal. And that is easy because the second property is saying the following, that M dot is diagonal, then P dot and P dot prime is also diagonal. So remember the inverse map, how this inverse map was defined? At K0 level, K0 M to K0 rho. Basically M's sending to P minus P prime. So M was a diagonal, then this is also diagonal, both are diagonal. So this the 0 goes to 0. So basically this, in fact, this isomorphism also respect the modulo part. So that's why basically this implies K and rho is isomorphic to K and M. All right. So it's just a couple of checking and also formal checking. So nothing very. So what is the reference for this kind of this result? Actually, you can see this proof. The reference the following. You can check. Let me write down the reference. Then I'll stop. So the reference you can check this proof. Maybe this is Dr. Tom Harish. And the paper called Algebraic Proofs of of some fundamental theorem of algebraic theory. And that appeared on, I think, HHA, homology, homotopy, and applications. I don't know, maybe 2017 or 18, I don't remember the year, but anyway. So you can look at this paper, I believe. So whatever the proof I explained, it mostly comes. All right then. Thank you very much. I'll stop here.
Okay, so are there any questions? All right. If none, then let's stop the meeting here.
All right.
Thank you, Professor, for the lecture. It
All
was a
right.
wonderful experience for the audience, I guess. So
Okay.
we'll see you next week.
No, I'm not lecturing in next week.
Yeah,
My,
I mean to the
yeah.
audience, yeah.
Okay. All right.
Uh-huh.
All right. I'll
Thank you.
share this note. Yeah. All right.
Yeah.
Thank you. All right.